Hello, in this section I'm going to talk a little bit about infinite limits. Now, what that means is basically whenever you have that the limit tends towards a certain unbounded behavior, such as negative infinity or positive infinity. Um, the only other thing that you would need to know is that in some cases, while I might say that a limit is infinity or negative infinity, you have to take into consideration that the limit technically does not exist. So we can start by saying, like if we have the limit as x approaches 0 for 1 over x squared, we can ask ourselves this question as to like what does this go to? Now, interestingly enough, if you do the algebra, you end up getting 1 over 0, which in this case is undefined. Now, in most cases, this is enough. But if we want to know like the specific behavior, then that's where we have to talk about like is it minus infinity or positive infinity. So like for example, if we go ahead and we look at the graph of 1 over x squared, well, we'll kind of see that it looks something like this, where we have that it approaches the y-axis, and then we have something like this as well. Okay, so this is our function f of x equals to 1 over x squared such that x cannot equal to 0. Now, if we can kind of see, for example, like from the left side, so if we look at the limit as x approaches 0 from the left for f of x, we can basically see that it approaches um, positive large values or infinity. Similarly, if I look at the right-hand side of f of x at 0, well, I have that it's approaching positive values too, so that's going to be infinity as well. But together, both of these, because they're both positive infinity, that gives us that the limit as x approaches 0 for f of x is infinity. Okay, now that's kind of strange given that, you have that infinity is not a real number. So in that case, I would have to say that, well, technically that does not exist. So you have to take that into consideration as well, that even though I said infinity and this equal sign, this is more or less just notation. So another way that you could probably show it is if you look at, for example, like if you have that you know that you're going to look at 0, but you also want to look at point 0, 0, 0, 1, and then maybe like point 0, 0, point 0, 0, 1, and then maybe like point 0, 1, and then point 1. And then maybe you might want to do the same thing where you have like negative. So essentially, like you're looking at it from the same side. So you have negative zero point 0.1, negative zero point zero 0.01, negative point 0.001, and then negative 0.0001. And basically, you'd just be plugging these values in into the equation. So, for instance, we know that it's undefined at 0, but the question is like, what is it from the left and the right? So, for example, if I was to use my calculator, well, I can say, well, if I go to, like, say 1 divided by zero point 0.1 squared, well, I get that it's 100. But if I get that I enter smaller values, okay, not like that. Well, these values are just going to get bigger. So we have that it goes from 100 to 10,000. And then if we do another, such as like 1 divided by 0.001, and we square that, Well, now we have that that's going to be 1 million basically. So you can kind of see that these values are getting bigger, bigger and bigger. And you do the same thing for 1 divided by 0.0001, and you square that. And now we see that, well, we have 100 million. So we can actually go ahead and write that in our chart over here. So we have that this is going to be 100 million. We have that this is going to be, yeah, there's more zeros. This is going to be 10,000. And then we have that 0.01. Let's see, 0.01 gave us, hang on. So we have 10,000, and we have, that's supposed to be 1 million. Okay. So this is 10,000, 100 million. Okay, so 4, 5, and we'll just add another 0. Okay, so that should fix it. Oh, wait, one more 0. So let me just check that to be sure. Okay, so, and then yeah, this is going to be 10,000. And then, let's see, did I plug in? That's going to be 100. Okay. Now, technically, this is all going to be the same. We have that if we plug in this value, 0.01, that's going to give us the exact same thing. It's going to give us positive 100. And then we have that if we move it along, we have that that's going to increase in value. So we have 10,000, then we have 1 million, and then we have 100 million. So in that case, we can see that there's unbounded behavior for 1 over x squared where it's approaching positive infinity. Now, I can do the same thing with, for instance, 1 over x. So if we were to look at the limit as x approaches 0 for 1 over x, well, you would notice the same exact thing, that you get 1 over 0, which is undefined. Now, of course, if this was just asking for the limit as x approaches 0, then yeah, we would just say it does not exist. But if we wanted to know, like, for example, the characteristics similarly to the previous equation, like 1 over x squared, then in that case, we would have to look at we would have to look at the limit as x approaches 0 from the left, and we would have to look at the limit as x approaches 0 from the right for 1 over x, and then see what that gives us. Now, the thing though is that if we do this, well, in this case, we would have to basically kind of do the same thing. We would have to do, let's see, we would have to do like the plus or minus 0.1, plus or minus 0.01, plus or minus 0.001, and then plus or minus 0.0001. Then from there, we would have to go ahead and see like what's the behavior of this. So I'll just put try. But let's look at the graph of the equation. Well, if we look at 1 over x, we'll see that 1 over x kind of looks like 1 over x squared. It looks like, yeah, we'll just use a blue. It kind of looks something like this from x is positive, and then we have something like this for when x is negative. Now, we can see that if we have x approaches 0 from the right side, well, that's just going to give us infinity. But if we have that f of x approaches, or x approaches 0 from the left, we get that it's minus infinity. Now, due to the fact that these are both not the same, this tells us that the limit as x approaches 0 for 1 over x that this does not exist. Okay, so we have that it does not exist. But it's a lot easier, yes, to just say that, well, if you plugged in 0, then you would just get does not exist. But again, if you were trying to figure out the characteristic behavior, then yeah, you wouldn't do it necessarily just like that, just using the algebra. Now, let's go ahead and look at some more examples. Some of these we can do algebraically, and then some of these, we'll look at the graph. So for instance, suppose that we want to find the limit as x approaches 2 for 1 divided by x minus 2. Now, we can do this the exact same way, where we just basically just look at the graph, or we can plug it in, or we can actually just use kind of like looking at like the left and the right. Now, let's say that, for example, that we go ahead and we set up some of our values. So like if we have 1.9, 1.99, 1.999, we know that at 2 that it's undefined, and maybe like 2.0, let's see, if we only did 3 decimal places, then that means that it would have to be 2.00 and then 1. And then we have 2.01 and then 2.1. We can actually get closer if we want, but it's just preference really. Okay, so basically what we're going to do is we're just going to say, well, what if we just want to know like what is 1 divided by 1 minus 1.9 minus 2, which in this case that'll be 1 divided by negative zero point 0.1, which in this case is negative 10. So we have that that's just going to be negative 10. Okay, so we have that this gives us negative 10, but essentially we do the same thing for this one. We plug in 1.99 and we're going to get negative 100. If I plug in the next value, I'm just going to get negative 1000. Okay, so in this case, like we see that we're getting larger values but negative. And we can verify this like if we use our calculator and we have like 1 divided by 1.999 minus 2 and then just hit enter and we get negative 1000. Okay, so in this case I know that it's undefined at 2. So we have that that's undefined, but if you plug in 2.001, essentially you're going to get the same thing, like you'll get 1000 but positive, you'll get 100 but positive, and then you'll get 10 for this, which is positive. Now, what this is telling me is that essentially I have that there's two characteristics in terms of like the left and the right. So we have that for the first one from the left side, we have that it's going to minus infinity. But we have that for the limit as x approaches 2 from the right side of 1 over x minus 2, this is going to be infinity. So essentially, this just tells me that the limit as x approaches 2 for 1 divided by x minus 2, that this does not exist. Okay, now, of course, some feel that uh, when you plug in the 2 that yes, you would have gotten 2 divided by 0, and then you would have just said, well, that's undefined clearly. But for that matter, you'd have to just be careful with it because, I mean, really, you're just trying to see like whether or not it's going to be positive or negative, infinity for that matter, because that's essentially what it's like, what it's going to come down to is that, when you look at the graph of the equation, well, you have that there's this vertical asymptote at 2, and you have that the behavior of the graph, it looks something like this, and you're just trying to see like what's happening as you get closer and closer to 2. What the behavior of an asymptote is such that when you get closer to 2, the asymptote x equals to 2, It's going to go to infinity on the right side, but it's going to go to negative infinity on the left. Okay, so that's us kind of just using like numerical methods in this case that we're just going to analyze and see like what's going to happen as we get closer to 2 from the left and the right. Well, we have that we can actually look at, for example, another problem of which that we kind of just set up a little differently. Let's say that we have x squared minus 4x plus 3 divided by x minus 2, and this is going to be squared. Now, for this one, one way that we can look at this, for example, is that if we go ahead and we just plug in 2, well, what you're going to see, for example, is that when you plug in 2, you're going to get 2 squared minus 2 times 2 plus 3, all divided by 2 minus 2 squared, which this is going to give us, let's see, 4 minus, oh, there should be 4, yeah. Yeah, so that's 4 times 2, which is negative 8, and this is 3 plus the 4 is 7, so that's going to be negative 1 over 0. But this is undefined. Okay, now, of course, if I wanted to know the characteristic, so basically I already know that the limit does not exist, but for instance, what if we wanted to know what it tends towards? So in that case, like we would have to say, well, we know that we can just break this down into x minus 1 times x minus 3, and all of this is divided by x minus 2 squared. Now, if we were to basically kind of like set up some uh, very large numbers or even small numbers, we would actually see that there is going to be a pattern essentially. So we can do two things where we kind of look at when x is greater than 2. Now, if we're going to do that, it's going to be 2.0001, comma 2.001, comma 2.01, comma 2.1. Now, we can go ahead and we can find those values, for instance. Now, one thing that you should note is that this is always going to be positive. So we know that that's always positive. But look at these values. Okay, so if we look at these values, we're going to see that these values actually have that, for x minus 3, it's definitely going to be negative. So in this case, that's going to be negative, and this is going to be positive. So what that means is that if we go ahead and we plug in values for the limit as x approaches 2 from the right side, for our original function x squared minus 4x plus 3 divided by x minus 2 squared. Well, okay, so essentially I'm finding that it is definitely going to get smaller and smaller, which means that it's going to get bigger and bigger as we divide by that number. So that means that basically for x minus 2, which is always positive, we have that this is going to be, and I'll put that over here, x minus 2 greater than 0. For this one, we have that this is going to be negative infinity. Okay, and that's because we have that, again, 2.001 is bigger than 1, and 2.001 is smaller than 3. So in that case, we have negative large numbers. Now, we can do the same thing for when x minus 2. So we have that x minus 2 is less than 0, but you also have that x is less than 2. So that means that you'd be plugging in values like, let's see, you'd have 1.9, comma 1.99, comma 1.999, and then we can do like another, so like 1.9999. So we have like four nines. Okay, so in this case, like if we plug in these values into the function, well, you'll kind of notice the exact same thing essentially. You'll see that 1.9 is definitely greater than 1, and 1.9 is less than 3. So no matter what, it's actually going to be negative regardless. So we have that if we do plug those values in for x squared minus 4x plus 3, it's going to give us, and again, this is positive, it's going to give us negative infinity. Now, what that basically means is that the limit as x approaches 2 for x squared minus 4x plus 3 divided by x minus 2 squared, that's going to be minus infinity. So we have that it tends towards minus infinity. Now, if we want to, we can actually go back and look at, for example, the graph of the equation. So we have, let's see, x squared minus 4, no, that should be minus 4, x plus 3 divided by x, oops, okay, let's do this again. Okay, so this should be x minus 2, and we need to square that. Okay, so if we go to graph, and let's say that we go to like zoom fit. Actually, that's not good. All right, let's just do this. Negative 10, 10, and then we'll do like negative 15, and then, well, we'll do 15 for the max. Actually, we might need to do higher than that. We'll just do 50. And then we'll just do minus 50. So we can kind of see that the graph of the equation is actually approaching minus infinity from the left side of 2, and it's approaching minus infinity from the right side as we approach 2 from the, yeah, from the right. So in that case, that tells us that, yeah, we have that it's minus infinity. Now, of course, again, if you wanted to just know, like, okay, if we plug it in, what do we get? We get undefined, so hence limit does not exist. But again, if we were trying to look for the behavior, then we would probably have to break it down like this. Okay, now, if we go ahead and we look at another example where we just want to find, so let's say like the limit as x approaches 1 for x divided by x squared minus 1 squared. But I don't want to just find that one. I want to find another. So like the limit as x approaches negative 1 for x divided by x squared minus 1 squared. Now you'll notice that basically, well, you have two things going on really. You have that there's an asymptote at 1 and negative 1, but you also have that let's see, you also have that it's positive in the denominator, which basically means that this is actually way easy because we can actually just look at the graph of the equation. So if we look at the graph of the equation, we have that there's two asymptotes. There's one at 1 and there's one at negative 1. So we have, here's our asymptote we can put at negative 1, and then we could put another at 1. Now, if I go ahead and I draw my graph of this equation, we'll basically see that the graph looks something like this. And we have that over here on the right-hand side, it's always going to be positive for values that are greater than 0, so it's going to be positive. But I noticed that there's an x-intercept at 0, but that when it's negative. So in this case, I have that there's going to be something like this. Okay, so if we go ahead and we look at the graph of the equation, well, basically we can see that for the limit, as x approaches 1 for x divided by x squared minus 1 squared, well, for this one, it's going to be positive infinity. Why? Because as x approaches here, it goes to infinity. As x approaches here, it goes to infinity. But then if we look at the limit as x approaches negative 1 for x divided by x squared minus 1 squared, no matter how you do this, like whether you make a table or whichever, you'll basically find that it goes to minus infinity on both sides. So that means that it goes to minus infinity. Now, note that for both, you would have gotten, you know, you would have gotten 1 divided by 0 for this one, but this one you would have gotten minus 1 divided by 0. Okay, now in this sense, it's no coincidence that you can kind of see that there is a correlation that for 1 over 0 it's positive infinity, and then for minus 1 over 0 it's negative infinity. But don't be misled by that because, for instance, um, um, with like functions like 1 over x, it's going to be positive infinity, but only from the left, and it's going to be minus infinity, but only from the, actually, it's the other way around. We have that it's going to be positive infinity from the right, and it's going to be negative infinity from the left. So, yeah, you can kind of at sometimes use these types of problems where you're able to see automatically that it's infinity and negative infinity, but it just doesn't work out like as many times as you'd like. Okay, so just be careful with that. Um, and again, you could have used table values if you wanted to. Like for this one, you would have had to use like well, you'd have to use two sets basically. You would have to do like uh, well, since you're approaching one, so in that case, you'd have plus or minus zero point 0.9 plus or minus 0.999 plus or minus 0.999, and then you'd have to do like 1.001, 1.01, and then 1.1. And these are all plus or minus, hang on. Actually, I don't need these pluses. Yeah, yeah, it would just be these values, for instance, for example. But for the other ones, you'd have to be a little more careful. You would have, okay, so you'd have negative 1.1 comma negative 1.01 negative 1.001 comma negative 0.999 comma negative 0.999 and then negative zero point 0.9, and then you would just be plugging these in into this function, and then you would see like, oh, okay, they both approach infinity and negative infinity respectively. Um, Now, keep in mind that if you do want to use your calculator, you can utilize it in a sense that, if you have that the function is included in your calculator or entered, you have that you can actually just do something like this where you just plug in the different values as needed. So, for example, I can set the window to standard and see how my graph looks somewhat similar, but just not as good. So like if we go to second trace and we go to value, we can plug in values like, like negative 1.1, and it'll tell us exactly what that is. Um, let's see. Okay, well, yeah, if we plug in uh, like negative 1.001, we'll see that it gives us very big values. I'm not sure what was going on with the other one because this one is closer on this side. Okay, negative 1.1 might be too far actually. Yeah, okay. So it should be like 0.999. Let me see if I got that correct. Yeah, I guess you should just get closer as much as possible. And then, of course, if you plug in 1.1, you'll get this value over here. And then if you type in 1.001, maybe another zero, yeah, you'll see that you get a bigger number. So in this case, we know that it's approaching positive infinity um, as we plug in each of these values. So yeah, eventually you'll get that it goes to infinity and negative infinity respectively. Now, this last example that I want to put on here is mostly because, a lot of people think that when you take the limit and you have that it's undefined at a particular value, that it's automatically just going to be undefined. So what I mean by that is if I have a value of which that it's not undefined, if that makes sense, like 3 in this equation is not, it's not undefined because, for example, we can go ahead and we can simplify this into the limit as x approaches 3 for x plus 2 divided by x plus 2 multiplied by x minus 2. Now, what ends up happening is that you have two factors that cancels out, which it gives you the limit as x approaches 3 for 1 divided by x minus 2. But if you plug in 3, you're basically just going to get 1 divided by 3 minus 2, which is just 1. Now, of course, it really technically did not matter whether we simplified it or not. Why? Because I knew automatically that it was not undefined at 3. So over here, I know that it's undefined at 2, but that it's also undefined at negative 2. The logic is that 3 is not any of these two, so automatically I can just plug it in and just say, well, that's really just 5 divided by 5, which is equal to 1. So same thing. So in these cases, you just have to be aware of where the equations are undefined and would have unbounded characteristic behavior such as minus infinity and positive infinity. But in the case that it's not any of those values, then it's okay to just plug it in.